Okay, so today what we're going to talk about is polynomial approximation. Okay, and some of you have probably seen something like this before. This is going to be a little bit weird in the sense that, like, this is a cool thing to talk about now. We have all the tools to do it. We are going to revisit it when? Sometime in March, I think. And we're going to do it in a little bit more detail then as well. But it's kind of a nice thing to introduce now. And like I said, we have all the tools to do it. Okay, so this is polynomial approximation. Okay, and there's lots of reasons why we might want to do this. Polynomials are very nice. They're very easy to work with. Computers can, compute polynomials and outputs of polynomials very, very easily. So those are all reasons that we might want to do some sort of polynomial approximation. But one of the things that you have to worry about when you do an approximation is figuring out, are you a good approximation, right? What does it mean to be a good approximation and these sorts of things? So let's define some things. Now, I don't think I've formally defined what it means for a function to be Cn. So let me do that first. So a function f is Cn on, let's say, an interval I, if f is n times differentiable. All right, just hold on a second here. N times differentiable. And the nth derivative is continuous. And all of that occurs on the interval I, right? So we talked about C1. We said you were once differentiable and the derivative was continuous. So Cn is the exact same concept, but you can do it n times, right? And note that, yeah, saying that your Cn implies that your nth derivative is continuous. Now, certainly all of your those lesser derivatives are continuous as well, right? So if you're 5 times differentiable, the fourth, third, second, and first derivatives are all continuous as well, because we know that differentiability implies continuity of the original function, right? So you do get continuity for all the previous derivatives, but you don't necessarily get continuity for that top order, right? For that nth order derivative. So it's kind of important to be able to specify it. And then one last thing is that we'll say that your function is C infinity. That f is C infinity on I if, it's completely differentiable. It's infinitely differentiable. I.e., it's Cn for all that. Right? And again, if you're infinitely differentiable, you don't need to worry about a continuity statement because you can guarantee that you're always going to be, all of your derivatives are continuous. Because if you want to know if the 10th derivative is continuous, you say, oh, well, look, I can differentiate the function 11 times. So the 10th derivative must be continuous, right? That's a sort of idea there. And so what is our goal? Okay, so we want to find a polynomial. So let's say we fix a function and we fix a point. Let's fix a function f and a point A. And what we want to do is find a polynomial which is a good approximation to f at A. A polynomial which is a good, because we don't know what that means, approximation to f at A, right? Okay, so that's our goal. So what we're going to do is we're just going to, write down a generic polynomial. So let's say define, this is just notation here, just so I don't have to write this down a million times. Pna of x is going to be the sum from k equals 0 to n, ck x minus a to the k, right? And in case you're just like, oh yeah, what the hell does sigma notation mean again? This is going to be, C naught plus C1 x minus a plus C2 x minus a squared plus dot 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 plus Cn x minus a to the n, right? All right. So our goal here is to figure out what should the coefficients be, right? So what are the coefficients? Or let's say maybe how do we choose the CK to approximate a function f, to approximate f at a. Okay, now there's no reason that you have to write the polynomial in terms of x minus the powers of x minus a, right? Like I've chosen to do that. We could have just said C1x, C2x squared, C3x cubed, so on and so forth. But to make it so that it has a 0 at A is going to actually be really, really important. So it's one of these, I've done the work ahead of time. I know that it's going to be useful to make sure that my function is actually, almost everything cancels out at A. So that's why we're going to write it like that. And you'll see why later. Again, you don't have to do it. It just makes the math a lot trickier if you don't do it. Okay, so that's the reason why we've done that. So our question then is, what makes a good approximation? So question, what makes an approximation good? Right? Because if we know what a good approximation is, maybe that will help us figure out what the coefficient should be. Right? And so the answer to this question is going to be the following. What we're going to do is we're going to compute the error. Okay, I'm going to define this as Rna of x, and that's going to be f of x minus our approximating polynomial, right? So this is the error, right? It is the difference between the function's value itself and what the polynomial approximates it to be. So this is the error. The reason why we use R is we often call it like the remainder, right? So this is the error. Right? Or remainder. That's why we call it the R. Now, some people will put absolute values around it, but like we're not going to do it. What do you mean by finding a polynomial? Right, and that's it, exactly. We don't know what the answer to that question is yet, right? What is a good approximation? We don't know. But so what I'm going to do is I'm going to show you what a good approximation is, right? So what we're doing is I'm going to define the error, and what we're going to demand is that the error goes to 0, right? And it should go to 0 near A. So we're going to demand, right, because this is the error, we will demand, at the very least, that Rna of A should be equal to 0, right? That if I'm doing an approximation to the function or at the point A, that the polynomial should be exactly equal to the function at that point. Nearby, they might start to differ, right? And it's only going to be an approximation. But at the point that we're approximating at, that at least they should be equal. Right? That's the same thing as saying f of A is Pn A of A, right? So at the very least, that should be true. Now, we can impose much better restrictions, though, because you imagine this isn't very restrictive. If all we do is demand that the remainder has to be equal, these two things have to be equal at a point, well, then your polynomial could do any sort of thing, as long as, if you think of their graphs, as long as the polynomial passes through A comma f of A, then you're good, right? And obviously, we need to impose something a little bit more strict than that. So what we're also going to say, or maybe kind of like, yeah, let me put this as like a bullet point. So we will say that Rna is a good linear approximation if its error disappears faster than linearly. If its remainder RNA vanishes faster than linearly near A. Okay, and the way that we write this is in terms of a limit. Like that. Okay, so what we're saying is that if you were to write out what this remainder is, right, again, it is the error. And the error term vanishes so quickly that if you divide it by x minus a, which is a linear term, right? X minus a is linear. If you divide it by x minus a, it's still going to 0, right? So it's a good linear approximation because the error is at least linear, right? Does that kind of make sense? People understand what I'm saying there? Right? Because when x is close to a, you imagine that, like, well, how do I say this? This might make a little bit more sense when we get into like the higher order approximations, but do you see what I'm saying here? Yeah, exactly. It does kind of, exactly. It looks kind of like f prime of a, but like we don't, it's a little bit circular, Stephen, because you know where it's going. I think, right? You know where it's going, so you know what the answer I think is going to be. And it's true that it does end up looking like f prime of a. But again, it's a little bit circular because we're doing the derivation of the fact that f prime is a good linear approximation. Right? Okay. And so same sort of thing, like higher order, what we're going to say is that it's a good quadratic. And then I'm going to write out quadratic. And then we're going to talk about, you know, being a good kth order approximation. Right. So RNA is, I'm going to write this one a little bit shorter. I don't want to write out this whole sentence. Is a good quadratic approximation near A if the limit, and you can guess what's going to happen, right? We're going to put x minus a squared down here is equal to 0, like that. Okay. And so in general, you're going to be a good kth order approximation if you take your remainder, you divide it by x minus a to the power of k, and that thing's equal to 0. Right? So in general, RNA is a good kth order approximation if the limit as x approaches a of the remainder to the power of k is equal to 0. Okay. And again, so here's the thing that you can think about. Like the remainder, so as x approaches a, x minus a becomes very, very small. And so therefore, when you take high powers of it, the high powers of it become even smaller, right? So a small number raised to the power of 10 is a really small number, right? A number less than 1 raised to the power of 10 is very, very small. So these errors are going to 0, right? The thing that we're dividing by is going to 0 very quickly, right? Like if we talk about a 10th order approximation, when I divide by x minus a to the power of 10, the denominator is going to 0 very quick, right? So x is getting really close to a really quickly. So this makes the remainder a better and better approximation because we're saying that the remainder goes to 0 faster than that, right? Does that make sense? Right? X minus a to the power of, 10 goes to 0 really quickly, right? Really quickly. So the remainder is going to 0 even quicker. For this limit to be 0, the remainder has to be going to 0 even faster than that. And that means that it's a good approximation because if your error is approaching 0, right? Again, away from A, we have no guarantee. They're probably not equal, right? The remainder and the function aren't going to be equal, but the polynomial might do such a good job of approximating your function that its remainder is very, very small and is going to zero faster than x minus a to the k. So that's the idea there. All right. And if you have any questions about that, don't hesitate to answer. It's not like crazy critical, but it's going to motivate how we choose our coefficients. All right. That's the idea. Okay. So the claim that I have that I am going to make and subsequently prove is the following. So claim, if P and A is a good kth order approximation. Oh, sorry, these should be P and A's, right? The polynomial is a good approximation, not the remainder. Did I do that? Yeah, the polynomial is a good approximation. So if P and A is a kth order approximation to F, then the derivatives of the remainder terms are 0 at A for all A from, or for all J, the derivative from 0 to K. Like so. Okay, so what I claim is that this condition, right, that Rna over x minus a to the power of k being equal to 0, that is the same thing as saying that the derivatives of the remainder term all vanish for the derivative from the 0th derivative. And here again, we assume that the 0th derivative is just the function itself. And then all of its derivatives up to k vanish at the point A. Okay? So let's check that. And again, kind of implicitly here, even to be able to differentiate this, right? In order to be able to differentiate the remainder, and remember, what is the remainder? The remainder is right here. So we kind of are assuming implicitly here that all along the way, F is sufficiently differentiable for us to even be able to talk about these derivatives, okay? So maybe I should explicitly say here, you know, suppose that F is at least CK. Right? So that we can at least differentiate it k times. And PNA is C infinity, right? All polynomials are C infinity. You can differentiate all polynomials as much as you want. In fact, maybe yeah, CK is fine. Okay, so let's show that if you're a good kth order approximation, that means that the derivatives of U vanish. So basically, so we know, let's say, what do I want to say? Right, let's do this by induction. And induction feels kind of like overkill here because we're only actually proving finitely many things, right? We're not like proving something for all natural numbers. We're only proving from j equals 0 to k, but we're going to induct on j. So let's start with j equals 0. Okay, and you're going to recognize this proof. This is the exact same proof that we use to show that differentiability implies continuity. So what I'm going to get is Rna of A is the limit as x approaches A, Rna of x. Okay, so that's true because the remainder is, in fact, continuous, right? The remainder is the difference between f and p, right, and PNA, and both of those functions are continuous, right? F is CK to begin with. So both of those functions are continuous. The remainder is the difference of those functions, and so is therefore also continuous. So when we want to evaluate this limit, we can just plug it in, right? And now what I'm going to do is I'm going to do our old trick of multiplying and dividing by x minus a to the k. Rnax x minus a to the k times x minus a to the k. Both of these limits exist. Certainly x minus a to the k exists, but RNA over x minus a to the k exists by assumption, right? Because we've assumed that RNA is a good kth order approximation. So I can limit law this. And both of these terms are just going to become 0, so there isn't anything to do. We're just going to get 0 out. Right? Limit x approaches a, x minus a to the k. Both of these things are 0. So that gives me, right, if I look at, ignore all the middle stuff, just look at the beginning and the end. Okay, so the 0th derivative here is 0 at a. That's what we assumed. In fact, we'd already talked about this though, right? We kind of demanded that this was true, but now we can prove that this is true if you're a good kth order approximation. Okay, so inductively now, suppose that, so we're actually going to use strong induction, Rna to the j of a is equal to 0 for all j equals 0, 1. I need another letter. Let's maybe say m, and here m is less than k. So now I'm going to assume that all the derivatives up to the point m are 0, right? So this is the principle of strong induction. Hopefully you've seen this. If you're taking 102, you might have done it. We don't usually do too much strong induction in this class. This is probably the only point where we're actually going to do it, but this is a strong induction proof. And of course, strong induction is a misnomer because strong induction and induction are exactly the same. Okay, and so now what I'm going to do is I am going to, how do I want to do this? Yeah, let's just start at the beginning. So I'm going to say 0 is now equal to the limit as x approaches a, Rnax. Okay, so I'm not doing anything. I'm just writing out what it means to be a good kth order approximation. And what we recognize is that by assumption, this is indeterminate type 0 over 0, right? For like L'Hopital's rule. Right, this is this type 0 over 0. So we can apply L'Hopital's rule to it. All right, that was the last thing that we talked about on Thursday. Right, and this thing again is type 0 over 0, right? Because by our induction hypothesis, we've assumed that all the derivatives up to m are 0 at our limit point, right? And the denominator x minus a to the power of k minus 1 certainly not, certainly also is approaching 0. So we can just keep on doing this, right? We can keep on applying L'Hopital. Maybe let me do one more before I do my ... Oop, I got to put my limit in. Limit as x approaches a, Rna double prime, k times k minus 1, x minus a to the k minus 2, right? And I can just keep on doing this because I got type 0 over 0 all the way until I get to the jth derivative. All right, so let me see. So I'm going to get Rna to the power of j x divided by, what is this nasty term? So this is, if that's k minus first derivative, so it's going to be k minus the number of derivatives. Right, okay, so it's going to be k factorial, k minus j plus 1 factorial, x minus a to the k minus j. Right? So let's just double check this. So in the second derivative, I've got 2 factorial, or sorry, I've got k factorial divided by k minus 2 plus 1 is k minus 1. Oh no, it should just be k minus j. Right. Right? So we've been just repeatedly applying L'Hopital up until this point. We get to this. This is our final 0 over 0 form. So I can apply L'Hopital one more time. And now here is where we're going to get, or sorry, not J. I think I've been using M. And so here is where we're going to learn about M plus 1. So this will give me K factorial, K minus M minus 1 factorial, X minus A to the K minus A minus M, or sorry, K minus M minus 1, right? And so the claim is that, again, ignore all the middle stuff. What do we have? We have this nasty limit here is equal to 0. And now what we do is our same trick. Thus, the limit. So again, this is continuous. Rna m of x. And then we're going to multiply and divide. So to the K minus M minus 1, or I guess this should be M plus 1, because that's what we're proving now. It's getting a little bit messy. Divided by X to the K minus M minus 1, right? Times X minus A to the K minus M minus 1, like that. Again, both limits exist by assumption. So I can break this up using the limit laws. I don't want to write all this down again, but what can you do? Things we do in the name of rigor. You're all smart. I probably could have just said by the limit laws, this is equal to 0. Okay, and again, this is equal to 0 because both of these limits is equal to 0, right? Yeah, the thing that I've underlined in yellow has this nasty K factorial over K minus M minus 1 factorial, but again, that whole limit is equal to 0. So by the time you factor out that limit and put it on the other side, it doesn't actually contribute to anything, right? So inductively, we've now proven this up until, we assumed it for M or up to M, and then we proved it for M plus 1. This is going to hold as long as we can do this. And as long as the function is ck, we can actually do this all the way up to k, right? So we've now proven the result that we wanted to show, right? So thus, we've shown that R n a j at A is equal to 0 for j is 0, 1, all the way up to k, right? Okay, any questions? It's a little hairy, right? All of that just to be able to argue, hey, at the end of the day, the derivatives of the remainders must go to 0 or must actually be 0 at the point. But that's the critical step, because that piece of information is going to tell us exactly how we should choose our coefficients, right? Knowing that the derivatives must vanish at A is exactly how we're going to choose our coefficients, all right? So we have to figure out what this means now. So now that we know that all the derivatives have vanished, how do I get K factorial over K minus M? Sure, okay. So basically, here, actually, I'm going to write down something else as well that's related to this, and it will hopefully clear it up. So yeah, let me say this. Okay, I'm going to use this in a second. So let's think about it. If I took like 3 derivatives, here, let's do this over here. So let's say I took 3 derivatives of x minus a to the k. What do I get? So I get k, k minus 1, k minus 2, x minus a to the k minus 3, right? And so my goal here is that I don't want to write this as, k times k minus 1 times k minus 2 dot, 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 dot. So what I'm going to do is I'm going to write this as k factorial, right? Which we know is k times k minus 1 times k minus 2, so on and so forth. But then I say, listen, why don't we get rid of everything after k minus 3? Right? Because if I do that, I get k times k minus 1 times k minus 2 times k minus 3 factorial divided by k minus 3 factorial, right? Those things cancel. And now I'm just left with the thing that I want, k times k minus 1 times k minus 2. Does that make sense? Okay, cool. Right? So that's where that comes in. Okay, so thus we've shown that the remainder is 0. And again, if we translate that, so that is, well, R and A, if we take jth derivatives of this function, that's just going to be fj, right? The jth derivative of f minus the jth derivative of our polynomial at A. And we can't really say anything about f until we know something about f, but we can say something about the polynomial, right? So let's look at this thing, right? Let's look at the polynomial. So note that d to the k dx to the k x minus a. Do I want to switch? Okay, yeah, whatever. L is equal to, so what is this? L factorial divided by L minus K factorial for the same reason that we just talked about. So that's if K is less than or equal to L, and 0 if K is greater than L. Okay, does everyone agree with that? Right, so that's exactly the conversation that we just had above, right? Which is if you take L derivative or K derivatives of the Lth power, well, first of all, if you take more derivatives than there are powers, eventually this will become 0, right? So that's that second line of the case. If you take fewer derivatives, then you just basically get L times L minus 1 times L minus 2. I've kind of switched between whether I'm writing it in terms of Ks or Ls. I'm sorry for that. But yeah, so this is the formula. We've seen this just a second ago. So this is true, right? And what we can do is we can use this. Oh, maybe I should write it as the jth derivative. No. Okay, whatever. It is what it is. Should I write it in terms of the jth derivative? Yeah, okay, you don't have to do this if you don't want to. I might just, because we're going to take jth derivatives, and I think I originally wrote my polynomial as being indexed in k. I might switch this around. Like that. So if j is less than or equal to k, j is greater than k. Okay, so if you wrote this down, don't rewrite it. It's not worth it. But I just changed the formula, so I changed what k and L were doing. But it doesn't matter, right? Because they're kind of dummy variables in this formula anyway. All right, so thus, when I take the jth derivative of p n a of x, that is the jth derivative of the sum from k equals 0. See, this is why I wanted to use k here, because I think I originally wrote out the polynomial as being indexed in k. So that's why I wanted to do jth derivative of x minus a to the k. Okay, so this is a finite sum. So we can just take the derivative inside, right? Because we know that derivatives, the derivative of the sum is the sum of the derivatives. There's nothing crazy there. And I can factor out that coefficient as well. So d to the j, dx to the j, x minus a to the k. I can now apply that formula that I have above. So this is now actually going to go from k equals j to n, ck times k factorial divided by k minus j factorial times x minus a to the k minus j, like that. Okay, and so you'll notice that the bottom index, instead of now starting at 0, starts at j, because we know that all of those other terms have died, right? If j is bigger than k, then all those terms become 0, right? So your first order term dies, your second order term dies, your third order term dies, dot, 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 all the way up to your jth minus 1 order term. And then the first term that survives is the jth order term. Okay, now I, for one, don't really like this. So what I'm going to do is a little bit of summation magic, and I'm going to re-index this. Okay, and the way that I'm going to re-index it is to do the following. I need a new variable now. Maybe let's use L. So I'm going to let L be k minus j, right? When I plug in j, that's going to give me 0. And when I plug in n, that's going to give me n minus j. Okay, so my sum here, I will be able to rewrite it as the sum from L equals 0 to n minus j, c times L plus j. K factorial is L plus j factorial. K minus j is L. And then x minus a to the L, right? Like so. And voila, there I am. I have it. So, right, so this is the jth derivative of my polynomial, and it's a mess, right? It's this big long formula. But you remember back when we first started the lecture, I said, I chose to write this polynomial in terms of x minus a to the power of some stuff. And the reason that I did that is, well, look at what we would need to be true. It's this formula, it's the very first equation at the top of the screen. It's that because we know r sub n, Rn, I'm just going to call it r. We know that r of a is 0. So that means that f of a is going to be equal to p of a, right? Or the jth derivative of f at a is the jth derivative of p at a, right? So since the jth derivative of r of a is equal to 0, and that's equal to the jth derivative of f at a minus the jth derivative of p at a, look at what I'm doing. I'm plugging a into my polynomial, right? And if I were to plug that a into this polynomial, almost everything is going to become 0. The only thing that's going to survive is the L equals 0 term, right? The term that doesn't actually have it doesn't have an x minus a in it, right? So when I plug that in, I'm going to get fj a. So the L minus 0 term is the one that survives here. So that's going to give me cj, L equals 0. So that's going to be times j factorial divided by 0 factorial. So that's 1. And that's it, right? Here, maybe let me write it all in. 0 factorial x minus a to the power of 0. And so that whole thing is equal to 0, which means I can now solve for cj. And that is going to give me f to the j a over j factorial. Right? Voila. So now I've found my coefficients, and 0 factorial is just 1. Yeah. Right? There's a couple of ways that you can justify this, but usually if you take the combinatorial definition of factorial, it's the number of ways that you can choose something from a set with no elements in it. And there's exactly one way that you can do that, which is you choose nothing. Right? Which is maybe a philosophical question, but 0 factorial is 1. Yeah. Okay. Okay, sweet. So what that means, this leads us to our following definition. as we now have these coefficients. So if f is Cn at the point A, the nth order Taylor polynomial so that's what we're defining, to f at A is that thing, right? So it is the polynomial that we found, but now I'm going to actually plug in those coefficients into the polynomial, right? So instead of being ck times x minus a to the k, well, I know what ck is. I found it, right? I figured out what it was supposed to be. It was the kth derivative of f divided by k factorial. That is our kth order, or that, sorry, is our nth order Taylor polynomial. Okay? We'll compute one in a second. What we have to do first, though, is this doesn't actually prove that f is a good approximation. Believe it or not, all of this was just our motivation to say, like, yeah, listen, what we hope is that if you're a good approximation, this is true, right? So if you're a good approximation, this is the formula for the polynomial. But what we want to show is that if this is our polynomial, it is actually a good approximation, right? So we've shown that it is a necessary condition. We haven't shown that it is a sufficient condition. So if you're a good approximation, this is the polynomial. In practice, we want to go in the other direction because you're not going to know if your approximation is good to begin with. So in practice, we want to say, if you write out this polynomial, it is a good approximation, right? So all the work that we've done so far is the necessary condition. We now need to do a sufficient condition. To do that, we have to prove a theorem. Okay, and that theorem is as follows. And what you're going to see, I'll point this out actually maybe after I've written it. Suppose that f is Cn plus 1 on the interval I. Okay, Cn plus 1. This is important, not Cn, Cn plus 1 on the interval I. And A is some point in I. Okay, it's the point at which we're approximating. So if P and A is the Taylor polynomial, for f at A, R and A is the remainder, then for all x, in I, there exists some C between A and X. Feels like a mean value theorem statement, right? And I can't use inequalities because I don't know where X occurs. I don't know if it's to the right of A. I don't know if it's to the left of A. But what I do know is that it's in the interval I. So C is between A and X, wherever we put it. And then when we actually do the proof, I'm going to assume that X is to the right just to make life a little bit easier. So there exists some C between A and X such that R n, let me just make sure I get the formula right, R n A x is f n plus 1 C divided by n plus 1 factorial x minus a to the n plus 1. Okay, so important note before we prove anything. Even though f is class Cn plus 1, we're only taking the nth order approximation. Maybe I should say Taylor polynomial. Okay, so what this theorem is saying is that the Taylor polynomial is a good, by the definition we talked about earlier, is a good approximation if you're Cn plus 1. Okay, so even though there, because you're class Cn plus 1, we know there is a Taylor polynomial of order n plus 1. But what this theorem is saying is that if you want that Taylor polynomial to be a good approximation, that you need to just take the nth order polynomial. Okay, so if you take the maximum Cn-ness, the maximum differentiability, continuously differentiability of your function f, you have to use one less Taylor polynomial in order for it to be a good approximation. Okay, that's really, really critical here. Okay. Okay, so it occurs to me, I think where we are here is that maybe we should take a break. And we come back, I will try and prove this. I would recommend you try and prove it yourself if you're really brave and want to give it a shot. But yeah, let's take about a 10-minute break here and let's see, hopefully it gives you a chance to collect your wits about you. And yeah, what you can do is if you want to, you can compute a couple of these Taylor polynomials. They're not that hard to do. So you can compute a couple of these Taylor polynomials and see, what they actually look like. In particular, we don't have too many functions you could actually try. We have ourselves rational functions and polynomials and, a couple of trig functions, things along these lines. But if you choose a nice enough function and actually work it out, you could, right? It's not too bad. So give that a shot and kind of see what happens. Like I said, let's take 10 minutes here. We'll come back in 10 minutes. I'll prove this for you. The proof's a little bit long. It's not that long, but it's a little bit long. And yeah, and then, like I said, I'll do a couple of quick corollaries and then I'll compute for you an example. I'll do sine. Okay, so if you actually want to get ahead of me, you can do sine x yourself before we actually get there. Okay. All right, so 10 minutes. I've got 9:58, 9:59 by my watch. So let's come back at 10:09 and we'll resume then. Okay. And again, if you have any questions, don't hesitate to throw them in the chat and I'll answer them as I'm around. Okay, see you soon. Okay, so time to prove this theorem. This is going to use something from assignment 7, question 1 that you've been tasked with proving. That proof's not hard. That proof is actually really, really nice. But yeah, so let's go ahead and prove this now. So proof. And again, hopefully you've been just staring at it long enough. You're like, oh, okay, I understand more or less what's being said. Actually, I guess, let's kind of take a second and look at this remainder term. So it says that the remainder term has it looks exactly like the next term of the Taylor polynomial, except, okay, and this is very important, instead of the n plus first derivative of f evaluated at a, because we couldn't get that perfectly, we have to use c instead, right? So if this term right here, if that term was an a, this would actually be the next term in the Taylor polynomial, right? But it's not, because it has that c there. So this is, a very cool theorem if you think about it. It says that it has the same shape and it has the same form as the general terms of the Taylor polynomial at the cost of us having to make, this approximation. And again, everything about this screams mean value theorem, right? Because exactly the same thing when we were learning about the mean value theorem, I said the mean value theorem allows you to make these approximations exactly equal at the slight cost of, instead of using the point at which you're interested in, you have to use a slightly different point. And then as well, this, there exists a c between a and x that makes this true, right? So it kind of screams mean value theorem. And yeah, we're going to see basically that it comes in here, not directly. The mean value theorem is going to be hidden, but it is inside of here. Okay, so what I'm going to do is I'm going to assume that x is bigger than a. Okay, the proof when x is less than a is exactly the same. The proof for x less than a is almost identical, right? Almost nothing changes. The only thing, the advantage of saying x is bigger than a is that I'm actually going to be able to say that c is now between a and x, right? A is less than c is less than x. So we don't have to deal with this ambiguity. So this is the only reason that I'm doing this. Okay, and what we're going to do now is we're going to define a crazy function. And this is the hardest part of this proof, is figuring out what this, how we should define this function. So what we're going to do is we're going to define this function g of t. It's going to be r sub n a of t minus r n a x divided by x minus a to the n plus 1 times t minus a to the n plus 1, like this. Okay, and it's important here to realize x is fixed right now, right? X is a fixed number. So what we've done is, we've got this interval here. Maybe here's our interval I. Right? We've got some point A inside of I. And now we've got some other point X. And again, I've assumed that X is bigger, right? And now we're going to show, we want to show that there's some point C between A and X. So X is fixed, which is going to seem a little bit weird for the sake of this proof, because normally we think of X as being kind of the independent variable. But in the function that I've just defined, this g of t thing, t is the independent variable and x is a fixed constant, right? So x is fixed in that equation. Just kind of keep that in mind. Okay, and what we're going to realize here, so note that if I plug x into this, so what do I get? I get r sub n a of x minus r sub n a of x divided by x minus a to the n plus 1 times x minus a to the n plus 1. Lo and behold, something cool happens. So the x minus a to the power of n plus 1s, they cancel each other out, leaving me with just r of x minus r of x. So I get 0. Right? So basically, my function is 0 at the right endpoint by construction. Now I claim that g to the k of a is equal to 0 for all k equals 0 dot 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 up to n. Okay. And let's check that. That's not too crazy. So first of all, if we just, I don't really want to do this inductively, but at the very least, let's check g of a by itself. So let's check the k equals 0 case on itself, and then we'll differentiate and see that it does work out. So g of a, what are we going to get? So we're going to get rn a of a minus rn a of x divided by x minus a to the n plus 1, a minus a to the n plus 1. Okay, so this term definitely is 0 here, right? So this just leaves us rn a of a, but we know that that's 0, right? Like we said, if you're a good kth order approximation, or rather just by construction of the Taylor polynomial, this thing ends up being 0, right? Like, again, let's not worry about good approximations. The construction of the Taylor polynomial guarantees that this is 0, right? That RNA's derivatives all the way up to n are all going to be equal to f's, and so therefore it is just equal to 0. Okay? So this is definitely true when k is equal to 0. So now let's differentiate, right? So note that the jth derivative, so let's say taking the jth derivative gives, so gj at a, so that's going to be r n a j t minus r n a x divided by x minus a, right? Because all this term is just x's, right? And x is a constant. So this is all constant term here. And now we want to differentiate the t term. Where's the definition of g? There it is, the t minus a to the n plus 1 term. So what is that going to give us? So that's going to give us n plus 1, what was it? N plus 1 factorial divided by n plus 1 minus j factorial t minus, oh, sorry, let's just call this a. Let's not evaluate it a yet. T minus a to the n plus 1 minus j. So now if I plug in a, I'm going to get r n a j of a. Okay, this thing again still equal to 0, right? We said by construction of the Taylor polynomial, it guarantees that all of these things are 0. And then again, when I plug a into the right-hand side, again, it's guaranteed that this exponent here is not 0, right? So this thing is also 0, right? Because again, I'm only taking, right? Because my claim is that this holds for up to n. When I say I'm taking the jth derivative, that means I'm implicitly saying j is between 0 and n, right? And if you look at the exponent here, n plus 1 minus j, if the biggest that j can be is n, that guarantees that there's some t minus a which survives, right? It's never going to be an exponent of 0. It's always going to have a positive exponent. So that guarantees that that term also always disappears, right? So we're done our claim. So this is, we've now shown this for an arbitrary j. So it's true for all j's. So that completes the claim. So thus, let's just kind of remind ourselves what we said. Equals 0 for all j equals 0 ... k, or sorry, n. Okay, now if you look at assignment 7 question 1, so if you haven't looked at it, you should look at it now, but maybe let me just pull it up quickly and then that way you can see it. Where did I put it? All right, yeah, so let me just share this screen. Yeah, okay, so I'm just gonna pop the screen over for a second. So here's the assignment 7, right, that you're gonna be in charge of. So look at what question 1 says, right? So f is n plus 1 times differentiable. You've got 2 points whose values are equal, right? This is kind of like a Rolle's theorem. In our case, right, they're 0. And you know that the derivative at the left endpoint is 0 for all k from 1 to n, right? So this is exactly a setup that we're in, right? In fact, maybe let me zoom in a little bit. So question 1 is exactly, I've just proven that G satisfies the hypotheses for us to use question 1 here. So what are we going to be allowed to do? So you're going to show in the assignment that there exists some C such that the n plus first derivative is equal to 0. So we are going to now apply this to G, right? So by this result, by assignment 7 question 1, there exists some C in AX such that the n plus first derivative of G at C is equal to 0, okay? All right, now I have to reshare this screen. Okay. Excuse me. So I'm literally just going to say by assignment 7, question 1. So by A7, question 1, there exists a C in the interval AX, right? Because we don't have A and B. We have an A and an X for this problem, such that G to the n plus 1 of C is equal to 0, right? Okay, so what is G to the n plus first derivative? So G to the n plus 1 of, well, again, let's just do it at t first, is r to the n plus 1 minus rnax divided by x minus a to the n plus 1. So now, right, normally this next term is t minus a to the power of n plus 1, but I've actually differentiated it at n plus 1 times. So that gives me n plus 1 factorial, period. There's no more t minus a's surviving, right? It's like if you have, t minus a to the power of 4, and you differentiate that 4 times, the answer is just a constant, and it's precisely 4 factorial, right? So we just get n plus 1 factorial here. Now, here's the other interesting thing that we have to think about is this Taylor remainder term. And again, remember, we said that f was n plus 1 times differentiable, and so we are allowed to differentiate this thing. But we only took the nth order Taylor polynomial, right? Which means that if you differentiate a degree n polynomial n plus 1 times, what do you get, right? If you have degree n polynomial and you differentiate it n plus 1 times, what is it? It's 0, exactly. So this term here is just fn plus 1. Right? Because let's double check, right? I'm not saying that RNA is equal to f. It's really f minus the polynomial, but I've differentiated n plus 1 times. So the polynomial just vanished, right? And the only thing that survives is the n plus first derivative of the function f, right? So there's some value c such that this is 0. Thus, g to the n plus 1 c is equal to 0. That's fn plus 1 of c minus r sub n a x, x minus a to the n plus 1 times n plus 1 factorial. And if we solve, oh, that's not what we're solving for. If we solve for r sub n a, we get exactly what we wanted. Right? Magic. Okay, any questions? And if you're writing, keep writing. What I had alluded to, and I guess, we should still actually prove it, but I said, if you're Cn plus 1, that guarantees that your Taylor polynomial is actually an nth order approximation, right? It's a good nth order approximation. There is a little bit to do to actually prove that. It's going to end up being one line, but we should actually formally prove it. I don't know if you can just see it. If you see this expression of the remainder and can be like, oh yes, it's obviously an nth order good approximation, but we can do that all the same. Could you explain how I get fn plus 1? Sure, absolutely. So, we have, so here's maybe just kind of like on an aside. So Rna of t is f of t minus Pna of t, right? So that means that when we take n plus 1 derivatives, we're going to take, it's just linear, right? So we're going to take n plus 1 derivatives of everything. Pna n plus 1 of t, like that. But Pn is an nth order polynomial, right? This thing is degree n. Right? And if you take n plus 1 derivatives of a degree n polynomial, it gives you 0. So that means that this whole thing here is equal to 0, right? The polynomial is equal to 0. So that just leaves fn plus 1 of t like that. Does that make sense? No problem. Okay. So, like, that's a bit of a magical proof. I wouldn't expect any of you to reasonably be able to come up with that. That's pretty tricky. But yeah, what immediately we get from this is the corollary that a function which is Cn plus 1 is a good nth order approximation, right? So let me just make sure I state this how I want to. If f is Cn plus 1, yeah. So corollary is Cn plus 1 on I. A is an element of I. P and A is the Taylor. Unfortunately, when you state theorems, you have to like state all your conditions again, so it's quite laborious. Taylor polynomial at A, then P sub n, and again, right, I'm assuming f is Cn plus 1, but only taking the nth order Taylor polynomial, then Pna is a good nth order approximation. Okay, and the proof of this is very quick. So by the theorem, there is some C, or how do I want to say this? I should, let's be more careful than that. So let's say, let RNA be F minus PNA, right? To just typically set up our remainder. So we want to show that this thing goes to 0 when divided by x minus a to the power of n, right? So we're going to have that the limit as x approaches a, RNAx divided by x minus a to the n is the limit as x approaches a, cx divided by n plus 1 factorial times x minus a. So this is using the theorem. Okay, so a couple of points to make here. First of all, I know that it's actually x minus a to the n plus 1, but we're dividing it by x minus a to the n, right? So I've just canceled those two things out ahead of time. I didn't want to write the whole thing out, so I just get x minus a. The second thing is that I've written c sub x instead of just c, right? And the reason for this is that this does depend on x, right? This is in the interval ax and depends on x. Right? But here's the important point. As x approaches a, and again, I've kind of written it so that, x is to the right, but we know that the theorem holds for both directions. As x approaches a, cx will also approach a, right? And fn plus 1 is continuous. So maybe let me write this down. So note that the limit as x approaches a of cx is equal to a. And since fn plus 1 is continuous, right, because we assumed that f was cn plus 1, that means that the limit as x approaches a, f to the n plus 1 cx is actually just equal to f to the n plus 1 of a. Okay, so this limit exists. And so in particular, if I continue on my sum, so this is kind of just like a side thing. I get the limit as x approaches a. Well, I can pull out the n plus 1 factorial. It doesn't really matter. Right, I just wanted to show that this limit existed. It's not going to matter though, because this term is going to go to 0. And now we're done. Okay, any questions? Is everyone okay why Cx goes to A? Right, it's basically a squeeze theorem. If you really want to write it out, you can. But here's A, here's X, right? And then Cx, you're guaranteed lives between, right? That's what the theorem says. The theorem says that Cx is between A and X. So you're always guaranteed, right, that A is less than Cx is less than X. So as X approaches A, Cx gets squeezed, right? It's a squeeze theorem argument. So you get that Cx approaches A as well. Therefore, since f is continuous, you can now change the variables and you get that that thing actually converges to whatever fn plus 1 at A is, right? Again, it doesn't matter what its value is because we're going to multiply it by 0. But in order to apply the limit laws, we just needed to guarantee that the limit actually existed, right? We do know that it exists. So voila, who cares what it is? And we get 0 as we want it. Okay, so any questions about that? Okay, sweet. So again, if you know that your function is Cn plus 1, that guarantees you that the nth order Taylor polynomial is a good approximation, right? So now we have kind of a necessary and sufficient condition at a slight cost that we needed Cn plus 1 in order to guarantee nth order good approximations. So we can't avoid this, right? There's nothing we can kind of do. However, this is nice, especially since many of the functions that we're going to play with aren't just Cn, but they're actually C infinity. And if you're C infinity, this means that every Taylor approximation is every Taylor polynomial is a good approximation to whatever degree that you want, right? If your function is C infinity, then you can use any n that you like, and it ends up being a good approximation. That's a really nice thing, right? Okay, but let's do an example. Let's compute something here. Okay, so example, let's say find, the Taylor polynomial for sine x. So let f of x be the function sine x, right? Let's say find the nth order Taylor polynomial. So we're going to do it for general n. Find the nth order Taylor polynomial for f at 0. Okay, and we're going to do it at 0. Lots of things are done at 0. A lot of people, you might hear the word Maclaurin thrown around when you do approximations at 0. This is all stupid. It's just everything is a Taylor polynomial. Okay, so we want to find the nth order Taylor polynomial for sine x at 0. We know exactly what the expression for the Taylor polynomial is, right? So we know that Pn0x is going to look like the sum from k equals 0 to n, f to the k at 0 divided by k factorial x to the power of k, right? Because a is 0 in this case, so we get a lot of nice cancellation. And so the only thing that we need to do in order to figure this out is figure out what the kth derivatives are, right? So we need to find f to the k at 0 in general. And there's no guarantee that you can do this. Like if you're given an arbitrary function, unfortunately, the higher order derivatives usually don't have any nice symmetries to them, and it's impossible to write them down in general. But for a couple of nice functions like sine, that is definitely possible, right? So let's start computing derivatives of sine at 0 and see what we get. So we're going to get f of 0 is just sine of 0, right? So that's 0. Now the derivative of sine is cosine. So if I plug that in, I get 1. Second derivative is negative sine. All right, that gives me 0. F triple prime is negative cosine. Oop, that's the theta. Let's 0. That's going to be negative 1. And then the pattern repeats, right? Like the derivative of negative cos is sine, and then we restart, right? We have this fourfold periodicity in the derivatives, right? So then repeat. So what we end up getting is that we note that the derivatives are only non-zero for or for odd numbers, right? So f to the 2k of 0 is equal to 0 for all k, right? That just says all the even derivatives are 0. And then f to the 2k plus 1 of 0 is equal to 1 if k is, I think, even. Don't write this one down yet. I'm going to double check it. Yes, right? So it's plus 1 if k is even and negative 1 if k is odd. All right, because let's see, what's the next one? F to the power of 5. That would correspond to k being equal to 2. That would be 1. Yeah, okay, so that checks out. Thus, it turns out it's going to be easier to write this Taylor polynomial as 2n plus 1. You could do it for general n if you want. It's just it is just definitely easier if we do an odd thing. So we're going to get k from 0 to n, negative 1 to the k, x to the 2k plus 1, 2k plus 1 factorial, like that. Okay, and again, you'll notice that here, so this is written a little bit differently than we're used to. Here, I have 2n plus 1, but up here, I just have n, right? So if we write a couple of these out explicitly, we'll get, for example, p1, 0 of x is just x, p3, 0. So there is p2, right? p2 does exist, but it is just the same as p1 because I just added on a 0 term. Right? So even though we're only writing out the odd powered ones, the even ones do exist. It's just that they're not special, right? They're just the previous odd powered one. Plus x to the 5 over 5 factorial, p to the 7. We'll stop at p to the 7. X cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, like that. And so you get this very nice symmetry, right? Where a couple things that we notice, the signs alternate, but here's kind of an interesting thing. We notice that only the odd powers survived, right? So first of all, this is going to finish this, but kind of interesting note. There are only odd powers in the polynomial. Right? And sine is an odd function. Right? Maybe that's just a coincidence. The fact that I had an odd function, and when I computed its Taylor polynomial, it only had odd things in its expressions, right? They all had odd exponents. And here's the interesting thing. So if you go and you try and do cosine, you imagine cosine is very similar, right? Because again, it has exactly the same four-fold periodicity. And so it ends up being very easy to write down. In that case, so what you'll find is that cosine only has even powers, and cosine is an even function. And it's not too hard to prove in general that odd functions about 0, right? So if you have an odd function and you take its Taylor polynomial centered at 0, that it will only have odd exponents, and even functions, if you take their polynomial at 0, will only have even exponents, right? And that this is just generically true. And in fact, is part of the reason why we talk about odd and even functions. You could say like, oh, why do we call them odd? Oh, because x cubed is odd and x to the power 5 is odd and x to the power 7 is odd, maybe. Or maybe there's something bigger going on here, which is that every single odd and even functions Taylor polynomial can be written as only odd or even exponents, right? That's kind of an interesting thing. So if you want to try something out here, I'd recommend you try that. Prove that the Taylor polynomial of an odd function is always odd, and the Taylor polynomial of an even function is always even. If you really want to go down a rabbit hole, one thing you might want to start doing is checking if you've got a good nth order Taylor approximation, a good nth order Taylor polynomial, is its derivative a good approximation to the derivative of your function, right? So if P approximates F, does P prime approximate F prime? Right? That's kind of an interesting question. And then if so, that would suggest to you that you could find the Taylor polynomials of some functions by differentiating, right? Especially where a function might be too difficult to explicitly compute its terms or to find a nice pattern. What if you could end up figuring it out by differentiating instead, right? This leads to a very kind of interesting question. Okay, so that's that. Now, I think something that's always worth seeing is these Taylor polynomials in action. Okay, so let me share something with you. You can find lots of apps that'll do this for you. And of course, you can just do them yourself as well. Okay, so here I am. I'm in Desmos. I literally just Googled, Taylor approximation. I specifically put in Desmos, but again, you can put in Taylor polynomial applet, something like that in Google, and you can get a million of these things. Okay, so I've chosen the function sine x, and I've chosen where I could center it, right? So I could center it somewhere else. I'm just going to center it at 0. Now I need to get this thing back to 0, like that. Okay, now here's the degree of the Taylor polynomial. So right now our Taylor polynomial is 0, so it's kind of stupid. And okay, when I set it equal to 1, remember, it's just x, right? The first order Taylor polynomial is just x, and this is exactly the line y equals x. And if you look, already you can see that actually does a pretty good job, right? As long as you're nearby, that does a really good job of the approximation, right? Probably to what? Pi over, what is this, 1.57 around here? So this is like pi over whatever, who cares? Anyway, it does a good job nearby. Okay, if I set n equals to 2, okay, nothing happens, right? Because we said the second order Taylor polynomial exists, but doesn't really add anything. Okay, third order. So this is going to be x minus x cubed over 6. Oh, look at that, right? Really nice. So here, let's go back between 2, 3, 2, 3. And so what I really want you to do is to look at here, right? So here is where our approximation really diverges, right? Our approximation is only good really close to 0, but it kind of diverges around here. This is where it starts to get bad. And as I bump it to the next level, it starts to hug the curve a little bit better, right? So if I move this up 1, yeah, look at that. Now you have to go all the way over here for your approximation to be bad, right? So the curve is much better. Again, 4 is not going to do anything, right? Because we don't add anything. Let's go to 5th order. And again, it does an even better job, right? Now it really is starting to look like between, negative pi over 2 and pi by 2, this is a really good approximation. We could even probably zoom in here. Look at that. Look how far I have to zoom in. And those things are practically overlapping, right? It's almost a perfect approximation. And sine's really not a nice function, right? Sine's actually really hard to compute. And so with only a 5th order polynomial, I was able to get a very good approximation all the way from negative pi by 2 to pi by 2, and so on and so forth, right? So let me just kind of move this up slowly, and we can just slowly watch this get better and better and better and better and better. Yeah, right? Isn't that cool? Look at this. By the time you're at 30, you've got this phenomenal approximation from negative 10 to 10, right? It does a phenomenal job. And so again, here's kind of one of the important things about this. Trigonometric functions are actually really hard to compute, right? It's really hard to compute sine of 5, right? If it's not some sort of multiple of pi, it's really hard to compute sine. In fact, so much so, especially for any of you interested in computer science or computers, there's this wonderful problem that Intel, their processors don't compute sine very well, right? So they have a logical set of instructions for computing sine x at the processor level. And it recently came out sometime within the last, I think, 5 years that they've basically been doing it wrong for, 30 years or whatever. And most of the time this isn't an issue, but some of the time it is. And that there are occasionally issues with Intel processors because they don't approximate sine very well. So sine is really hard to compute. But here's a cool thing. Polynomials are generally really easy to compute, right? Like if you think about what a computer is really good at, it's really good at adding things and it's really good at multiplying things. And exponentiation is just multiplication, right? If I take x to the power of 5, that's just multiply x by itself 5 times, right? So computers are very, very good at evaluating polynomials, right? Exceptionally good at doing that. So if you can take a function and you can write it as a polynomial, and we know, in fact, well, okay, I'll show you that in a second. If you can take a function and you can write it as a polynomial, then a computer can actually evaluate it very, very quickly. And as long as you make sure that you make the polynomial big enough so that it's a good approximation to your function for however much accuracy you want, right? Like if you're working on a calculator, you can only show 8 digits of accuracy sort of thing. If you just need 8 digits of accuracy, then you take like a 10th order polynomial, and the 10th order polynomial will basically give you 10 digits of accuracy. And voila, you've now used a polynomial to compute that instead of trying to compute it, you know, some other way. Like sine, like I said, sine is really, really hard to compute. So anyway, here's this like cool thing that I think, and Desmos is nice for this because you can actually change this function around too. Plus cos x. That's kind of boring. Here, let's maybe, so let's do like x sine x. Ooh, look at that one. That one's kind of weird, right? And same sort of thing, right? So here, and you can just like plug in different functions and mess around with this. This is always really fun to me. I always have a really fun time just doing these sorts of things, right? And you can, again, you can compute this by hand, right? X sine x, but you can really see it working. And then if we move the point around, right? So now what I'm doing when I'm changing a is I'm changing the point around which our approximation is centered, and you can watch the like polynomials move depending on where it's kind of centered around, right? I think that's so cool. Like I love doing this sort of stuff. It's truly one of the great wonders of having computers that, like, when you think about people who were first doing Taylor polynomials and stuff, they kind of had to visualize these things in their heads or, you know, plot them by hand. And you can imagine you're not going to do that for too many values. And here I am just moving my wrist a little bit and look at all this coolness, right? So the benefit of having technology is really cool. Here's an interesting thing. Look how well, yeah, this is weird. Look at this. Do you see how well this curve approximates it? This is pretty good, right? When I increase the Taylor polynomial, it actually becomes less accurate. And then it becomes super accurate, right? But there's a moment where it actually becomes less accurate and then way more accurate, right? Less accurate. So that's kind of a weird thing that happened, right? That's kind of a weird thing, but that's okay, right? Because it doesn't break the math. That's just a weird little thing that we noticed. Now let me kind of tell you this too, really, really quickly before we finish off today. I don't think I'm going to do anything too more hardcore, but you can use that thing that I just proved to put bounds on the error, right? So you could do something like, let's say you were looking at, and I'm basically just making this up on the fly, but you could use something like, suppose again that we have sine x. And let's say we limited our attention though, f between, I don't know, let's say -1 and 1. And this is sine x. So let's say I knew that the only numbers I could plug into sine x were numbers between -1 and 1 for whatever crazy reason, right? And you'll see that if you want to change that interval, it doesn't make a significant difference. You just have to make a slight change in what I'm about to do. So what I'm going to do is I'm actually going to say, I can actually bound what the error is, right? So suppose this is true and PNA is the, again, you know, the nth order Taylor polynomial. Maybe just let me write TV for Taylor polynomial. Okay, so the remainder term, so we know that for every x in negative 1, 1, or sorry, let's take our approximation at 0. Let's be specific about that. So we know that for every x in negative 1, 1, there is some cx such that the Taylor remainder, right? So this is the error term, right? This is the important thing to remember. This is the error term, is equal to fn plus 1. Here, let's actually put that in absolute values. It's the error when you put it in absolute values. N plus 1 factorial times x to the n plus 1, right? But now I can use a whole bunch of inequalities. So whatever the error is, that's going to be less than or equal to. Actually, in this case, it would just be equal to. So let me just kind of write this like this. Okay, n plus 1 factorial is already positive, so there's no reason to do that. Like this. Now, we know that the derivatives of sine are just sine and cosine, right? So we know that this term here is always bounded by 1. And this term here, the absolute value of x, well, we assumed our domain was negative 1 to 1. So this is also bounded by 1. And so this whole thing is just less than or equal to 1 over n plus 1 factorial. Right? And again, if you had a different domain, you can see that the only thing that changes, if your domain was like negative 10 to 10, you would have to bound the absolute value of x by 10 there, right? But what you can see here is that we get that the error in the approximation is less than 1 over n plus 1 factorial. And we all know, I think, right, n factorial grows really, really quickly, right? Really quickly. So what I've now guaranteed is that on the interval negative 1 to 1, the nth order Taylor polynomial will always be this accurate, right? It could actually be more accurate, but this is the worst, that it could possibly be. And, by choosing n to be sufficiently large, again, let's say I was programming a calculator and I knew that I only had 8 decimal places of accuracy that I needed to display, I could choose n to be big enough in order to guarantee that this always gave 8 decimal places of accuracy, right? In practice, if I were doing a calculator, I would do this between, like, say, negative pi to pi, and then just use, use the fact that sine is periodic to be able to compute where, the value of sine on all of R. So I'd say, look, let's use a polynomial big enough to guarantee us 8 decimal places of accuracy between negative pi and pi, and then let's use periodicity so that my calculator can figure out where the value of sine x is anywhere on the real line, right? And that's how you would actually program a calculator how to compute sine. Does that make sense? Does everyone see? And the only change you would make there is you would bound, so if you did f between negative pi and pi to r, x maps to sine x, right? The only difference now is you'd get RNA x is less than or equal to pi to the n over n plus 1 factorial. And you might be like, oh, hey, wait a second. Pi to the n probably goes pretty quick too. Yes, but n factorial grows faster, right? So you would just need to find an n big enough that this was less than 10 to the negative 8 or whatever. In fact, why don't I plug that into Wolfram Alpha? If any of you are faster than me, do it yourself. Like, what value of n makes this true? Stupid browser. Solve pi to the n divided by n plus 1 factorial is less than 10 e to the negative 8. Oops, I put negative 1. And it looks like, Wolfram Alpha, I don't like your answer here. Okay, Wolfram Alpha apparently is having a lot of trouble doing this. even though this shouldn't be hard. We could just graph it if we really had to. Anyway, hopefully you believe n plus 1 factorial is going to go to 0 much faster than pi to the n, so you can find an n for which this is true. All right, okay, let's try something slightly different. Oh, it actually is saying, oh no, yeah, there it goes. It gets quite small. Equals 10. Does it? Sweet. Yeah, I mean, that I guess is actually another way you can do it, is you can just plug in numbers. Nice. Yeah, X actually, it keeps giving me negative answers, and I want it to give me positive answers. So it's driving me insane. But yeah, you can just plug in numbers and see what works as well, right? So yeah, 18 decimal places, and you might be like, okay, wait a second. 18 is actually a lot of like decimal place. There's a lot of polynomial that I have to write out. But first of all, sine has a really nice, again, expression for its Taylor polynomial. So it's very easy to compute. And then second of all, it's like, again, a computer doesn't care. Like, this isn't hard for a computer, right? If you ask a computer to multiply a number together 18 times, that's easy for a computer, right? A computer can do that in a fraction of a second. And I'm not necessarily saying that this is the best way to tell a calculator to compute sine, but you can imagine that this is a very realistic way of having a calculator do it. And I think, if I asked you how does a calculator actually compute sine before this, if you didn't know about Taylor polynomials, it'd actually probably really be not certain, right? Like, what would you do? So this is kind of the power that Taylor polynomials gives you. Okay, so are there any questions? Everyone's happy? Okay, cool. So that's Taylor polynomials. Now, I actually don't even know what I'm going to talk about on Thursday, because like I kind of did everything that I wanted to. Maybe I'll dive into Taylor polynomials a little bit deeper. I don't want to start next term's material. Here's kind of where we are in an awkward place, is that actually I'm done the material for this year. And the reason that that's true is in previous years, we wrote term tests during class time instead of doing 24 hours. And I didn't account for this. So what it means is that we basically have 3 lectures, right? 2 or 3 lectures that would have been test time that are now just free because we didn't write a test in them. Yeah, this is what I'm trying to think. So I'm debating what it is that I want to do. I mean, we're going to do measure theory next term. I don't want to start it right now. It's going to be practically the first thing we do next term, but it really does fit better into the integration chapter. So I don't necessarily want to start it now, if that makes sense, right? I want to leave it so that we can talk about it. And in particular, I don't want to start it now and then have you all forget it over the winter break. So we will do measure theory eventually, very soon, but not, I don't want to start it. So what I could do, what I'm thinking I'm going to do is I'm going to talk about topology a little bit. And I'm going to see how much I can do in like a week. And then probably not general metric space topology. I think that's going to be too tough for you in general. Well, not necessarily tough, but I just don't have time to do metric space topology. So we'll just do, yes, point set, but like only on Euclidean R. Yeah, that sort of stuff. And I'll just see how much of that I can get done. So yeah, let me be clear. Either way, I plan on finishing up next Thursday for sure, right? So next Thursday, December 2nd, I guess that is, will be the last day of class. We're not going to do anything on the 7th or whatever day that is. So for sure, we're not doing anything in the very last half week. Okay, so we're not going to do anything then. So the only question is what we're going to do for the next 3 lectures. And I think what I'm going to do is I'm going to talk a little bit about topology because it's just nice if you have it. So we're going to, and I think some of the people downtown are doing it. I know, I think Eckert talks about it, and so we need to at least say that we're better than they are. So we need to do that. But I might just decide to call it even next Tuesday. So next Tuesday, I might just be like, boom, 157 is done for the year. We'll see. Right. And then I'll just do office hours. Like, I'll still show up to class and people can drop in, but we won't learn anything new and it'll just be office hours. So I'm doing that a little bit by the seat of my pants. Like I'm going to make the call depending on, I'm going to plot out what the lecture will be like. And then, like I said, well, I'll kind of just make the call at some point and be like, yeah, we're done for the year. So yeah, we're looking, that I think is currently my plan. We'll use polynomial approximation later this year. So it depends on what you mean by year, not in 2021. But yeah, like I said, we'll use it again in like March. So in March, what we'll do is we will replace this n with an infinity. Right? And when you replace that with an infinity, the math actually gets a lot harder, significantly harder. But that's okay because it's still really cool and it's a lot of fun to do. But we need to build up a lot more things before we can get to the point where we can put an infinity sign there. Okay, everyone. So just keep you apprised of things. That is my plan. But this effectively ends the term test material. When I start talking about topology, whether or not that's on your final term test, which is next Friday, well, it depends on what we talk about tomorrow. I will say anything that I talk about, or not tomorrow, anything I talk about on Thursday is actually going to be fair game for the term test, but whether or not I actually put it on there or not is a different story. Okay. Anyway, I assume some people probably have to run, so don't let me ramble any more than I'm currently rambling. Thanks everyone for coming. I will see you on Thursday. Thank you. You too, you too.